Alright, so we're going to do a lesson on molecular geometry. For this unit, you'll need a couple of handouts. The first one you need is titled VSEPR and Molecular Geometry. It looks like the standard set of notes that we usually do in class. And also the handouts on the reference tables. They're titled as a PDF, VSEPR. And that's a 3-page handout that you'll need. Alright, so let's go and talk about molecular geometry. Before we start, definitely you'll need to know how to draw Lewis structures, because without them you can't really do the rest of it. And after this lesson, you'll be able to learn how to use VSEPR that predicts the shapes of molecules and bond angles, and you'll also have to know what electron domains are versus your bonding domains, and also versus anything that you have with lone pairs. So we'll address all of those in this little lesson. Let's go and talk about shapes in general. So based on your Lewis structure, you should be able to predict the shape of covalent molecules, and you'll be able to do that by the end of today, or end of this lesson. I've given you an example of a semi-poorly drawn Lewis structure right here at the top, and essentially with this, you would say, okay, well, with this shape, with this diagram, I should be able to figure out what the shape is, and you'll be able to do that soon. But right now, if I were to just kind of say what it was or predict the shape of this molecule, you'd probably say maybe triangular or something along those lines. But in fact, it's quite different. And we'll get there a little bit later. For now, though, let's go ahead and look at the rest of the terminology. The focus that I want to kind of bring up to you is that we're going to look at the geometry around the central atom, and I want to focus around this specific thing. We're not talking about the outer ones, but we want to kind of focus again on the central atom, so make sure you're very clear about this. You have to identify something called your electron domains, and this does include your bonding electrons, also your lone pairs of electrons. So any electron domain can be classified by either identifying the bonding domains or the lone pairs. All right, so make sure you know that you have both bonding and non-bonding lone pairs of electrons that are considered electron domains. So if you look at this structure over here, this is a bonding domain, this is a bonding domain, this is a bonding domain, and this right here would classify it as a non-bonding or lone pair domain. Also, if you looked at this, there are 4 electron domains because you have 1, 2, 3, 4 domains, or 4 regions where electrons exist. And that's what electron domains are. It should be known that groups of electrons in close proximity will probably repel each other, and this should make sense because electrons are all negative, so anytime they're close to each other, they're naturally going to repel. Now, how does that affect our molecular geometry? Well, that basically states that anytime you have a set of electrons that are nearby each other, they want to maximize their distance to minimize repulsion. Therefore, you have a more stable structure, and that's why you want them to be as far away from each other. And that's where this next term comes in, the valence shell electron pair repulsion. So this one again is usually abbreviated VSEPR and usually pronounced as VSEPR. So you say VSEPR theory. And this theory is used to predict geometries of molecules. And you're talking about shapes. You're talking about if it has a triangle shape, square shape, so on and so forth. Now, for the sake of understanding this here, let's go ahead and actually talk about something else. So I'm going to show you a little now, I want to show you a little diagram here, or at least, sorry, a little simulation here, which kind of represents the shapes and what we're talking about. So remember that we're talking about repulsion and whatnot. This right here is an atom, and nothing right here is going to be repelling because I haven't put any electrons on here just yet. Over here on the right, I'm going to go ahead and add some atoms. So let's just add one for now. So this, again, right here is a single atom that has been added to our central atom right here. This then represents my electron domain around the central atom. Obviously, this is considered more of a linear shape because there's only 2 things connecting it. So this right here doesn't have a whole lot of repulsion going on either because this doesn't have anything to repel. However, if I were to add a second atom, so come over here and push another one, where would you expect it to be? Hopefully most of you would think that this would kind of be on the opposite side of this one because it's going to also have its own electrons that will repel this. And in fact, you do observe that. So you put this on here and you see them, again, repelling from each other as much as possible. If I try to bring one closer to the other, it will, again, naturally and spontaneously push away from the specific electron domain I'm moving around. What happens if I add a third one? Well, let's see what happens. If I add a third atom here, well, you can kind of should be able to predict that it's going to be some sort of a triangular shape, and you see that here. Right, so the triangular shape here, again, formed by the atoms. Also, again, most importantly, is formed around the central atom. And you can see as you kind of move this around, it actually also is all in plane. So all 3 of these atoms are in the same plane. It's essentially flat. Now, the problem is though, when you start looking at this, you need to make sure you think three-dimensionally. So if I added a fourth one, what would you expect to see? Well, a lot of people would probably predict that it's a square, right? Naturally, you see, okay, you have three things here, they're as far away as apart to make a triangle. Four things then would make a square. But let's see what happens. If you add this and kind of see what happens there, it actually comes in and it sort of pushes these downwards a little bit. So in fact, you don't get a square. You get something called tetrahedral. We'll address that a little bit later. But just by looking at this, notice that you don't actually have that flat triangle anymore. You don't have that flat triangle anymore. So you see that there's a kind of a triangle base here, but there isn't actually a triangle anymore. All right, it's not flat. And because this pair of electrons right here kind of pushed these other three away. They repelled them because it came in close proximity. And you add a couple more, and you kind of start to get some other shapes, and you'll see that later. Now I want to back it up a little bit here. So let's go back to where we were originally, which is having three of these. Well, instead of just adding atoms, I can also add lone pairs. So I can add a lone pair specifically to my central atom. Let's see what happens here. Again, it's flat, and you kind of send one in here, and notice sort of same thing happened, right? So we had a flat triangle, and then all of a sudden this guy comes in and pushes it down the same way, right? Also because there's a bunch of electrons here, these are also a bunch of electrons, and they will all repel, so that's why it gets pushed downwards a little bit, and you sort of see a very similar shape to what you saw before. Back to the information at hand, you kind of recognize that there's some need for this, and it's kind of useful here. So let's say you have these two compounds, H2O and CO2. Well, kind of, if you look at it, sort of, you have two compounds, and both of them have three atoms, so it's very similar. Both compounds have two atoms of one element and one atom of another. So you see that hydrogen, there's two of them, and one of the other. For CO2, there's two of one atom and one of the other. All right, so what do you expect to do with the shapes, or get to the shapes here? In fact, it turns out that water is considered to be a bent molecule, while carbon dioxide, in fact, has something called a linear shape. All right, so again, just by looking at these two diagrams down here, it's also hard to know. It's also hard to know exactly what shape there is. These both look pretty straight to me, I can tell you that much. But in fact, this is actually bent, while this one is a flat linear shape, or straight linear shape. So let's kind of figure out how this is supposed to work. There's something you got to know called a formula type. So you have to determine the formula type of any single molecule. Let's go ahead and take a look at these. You have the central atom, which is represented by the letter A, the X, which is the number of bonding domains around the central atom. It's not the number of bonds, but the number of bonding domains. You can also view this as the number of atoms around the central atom too, right? Either one's fine. And then right here, E represents the number of lone pairs around just the central atom. Now, let's go and take a look at some examples here. In order to figure these out, of course, you have to be able to get the Lewis structures. So I'm assuming that you're able to draw these out pretty consistently. I'll start off with CH4 here. This is your methane. If I were to give this a formula type, I'll start off by just giving an A. Right? A again represents the central atom. There's always a C. There's only one atom in the center, so we always call that an A. Then with X, it kind of, again, also has to count the number of atoms that are around the central atom. So if you look at these, there are 4 bonding domains, 1, 2, 3, 4, or again, 4 atoms around the central atom. So we call this AX4. And E is the number of lone pairs around the central atom. But in this case, there's no lone pairs around the central atom, so we just leave it alone. We don't even write an E. The E is not even included at all. Looking at this one right here, you can probably get the idea of where this is going. So start off with A as your central atom for nitrogen, right here, it's central atom. X, you'll have 3. And then E, well, right here, you only have a lone pair, and that's going to be E with no subscript. All right, no need to write E1. Also remember that it's a pair of electrons, so make sure you don't confuse yourself and write E2. That's a very common mistake. Over here, you have this one right here, C double bond O to H and H. This is one of the examples we saw, not on this handout, but on another example from a long time ago. C right here is your central atom, so represent that with the letter A. I have 1, 2, 3 atoms around my central atom, or again, I have 1, 2, 3 bonding domains, right? Even though this is a double bond, this actually is a single bonding domain. All right, and since we have those three, we go ahead and label that AX3. And then with E, it's the number of lone pairs around the central atom. So in this case, you actually don't have any lone pairs around the central atom. I know you want to count these right here. It's tempting to do that. But remember, we're talking about the central atom, not the outer ones. So do not include these as part of your formula type. So your formula type then for this third one would be AX3. On your handout, you do have an example of H2S, which has the structure that looks like this. And just by looking at this, you should hopefully be able to also now get that the formula type is AX2, right, because of the 2 on either side, and then E2. Now, let's go and take a look at that chart that you guys have. Remember, this is the 3-page chart that is included with your handout. So this one, again, there's 3 pages to it, and I'll kind of organize it the best I can. I'm going to go and take a look at the first part of the handout. Is the first page, and I've kind of cut off the top introductory stuff, and I only focus on the bottom, this bottom right here. Again, notice that it has electron domain geometry. So we're actually going to have 2 different types of geometries that we'll focus on, and I want to make sure you're very clear about which one this specific chart focuses on. So please make sure if you need to circle the electron domain geometry in, a couple of times so you know clearly what this is looking for. Now, right here, the number of electron domains. So this is, again, how many bonding and lone pairs, bonding domains and lone pairs there are around the central atom. This second column right here is about the 3-dimensional arrangement. So what does it look like in 3D? And the electron domain geometry. So if I asked you again, what is the electron domain geometry, you would use any of these answers in this column that applies. And then the predicted bond angle is something we'll get to a little bit later. But for now, let's go and focus on this part here, number of electron domains. So notice it goes 2, 3, 4, all the way up to 6. So this is essentially the sum of what 2 parts of our formula type. So what 2 things does this incorporate? Well, since again, electron domains is made up of both bonding domains and lone pairs, this is actually X plus E. So whatever values you have for X and E, add those together and you get the number that would then correspond to some 3-dimensional shape here. Now these are useful to help you visualize what it looks like. Kind of notice that these little circles just represent the bonds, or atoms, and the lines represent the bonds. These again are all in a straight line, so 3-dimensionally it would look pretty flat on a sheet of paper. These right here also, again, kind of in a flat plane is what we saw earlier. Those are all on the flat sheet of paper, so that one, again, looks pretty okay there. But this one starts including more of a 3-dimensional look to it. So these 3 right here are all in the same plane. These are flat with the paper. But then you see this one and this one with the hash marks, one with a little wedge. The wedges kind of look like they're coming out towards you. They're skinnier towards here, at least they're supposed to be, and a little bit fatter out this way. So it looks kind of like it's coming out of the paper towards you. Whereas over here, the little hash marks kind of go into the paper. It looks like they're kind of going away from you. So it looks like it's going 3-dimensionally into the paper away from you, so you can kind of see the 3-dimensional shape overall. And this continues on with the rest of these. So you see these little hash marks and these little wedge, and some more hash marks and wedges as you go through here. All right, so this is, again, your electron domain geometry that incorporates all lone pairs and bonding domains. Now, again, looking at the answers, if I asked you again, what is my electron domain geometry, you'd go ahead and look through here. There's my linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. These are terms that you will have to know and memorize. And after some time, I will allow you to not look at this for tests and quizzes. All right, so again, linear, trigonal, planar, tetrahedral, trigonal bipyramidal, and octahedral. Linear, again, for straight lines. Trigonal planar means triangular, and it's flat for planar. Tetrahedral, tetra meaning 4, hedral meaning face, so there's actually 4 faces to this. Kind of look at it. There's one face that kind of is with this set of 3 atoms. There's another face kind of looking back into the paper with these 3. Right? So, and then you also have another face down here on the bottom, going this way, and then another face sort of going towards the right, maybe just a tad upwards. So that's another face. Anyway, 4 faces, tetrahedral. That's maximizing minimizing anyway the repulsion between each of these electron domains. Trigonal bipyramidal is kind of similar to trigonal planar, but instead of seeing it flat on the paper, they've sort of made it flat, or making it going into the paper. So this, and then you have the part that's go up to go down. So this is your triangle part right here. This is your trigonal part, and that's a plane. But trigonal bipyramidal, meaning there's 2 pyramids, so one going up and one going down. So this is a pyramid right here, one pyramid, and another pyramid going downwards. Octahedral, again, sort of the same logic as before. Octa meaning 8. Hedral meaning faces, and there's 8 faces here. So it kind of also looks like it's square pyramids. So, but 2 square pyramids, one above and one below, but that overall makes the octahedral shape.